Okay, Chapter 8, we're going to be talking about things going around in circles or things that are rotating. So I'm going to start off with a little bit about center of mass and talk about how circular motion really isn't all that complicated once we separate out rotation from translational motion, or things that are going round to things that are going side to side. I'll talk about how we can have inertia for things that are rotating, and then I'll talk about how we can get things rotating, so how we can apply a torque. I'll kind of come back to center of mass and center of gravity for just a teeny tiny little bit, and then I'll talk about the centripetal force and the centrifugal force, which is not a real force, and I'll kind of finish off by angular momentum, which, much like linear momentum, is going to be a conserved quantity. Now, things that are rotating, we're going to say that they have rotational motion, and that can be combined with translational motion. If you think about taking a wrench like this one right here and tossing it like that, and you could kind of picture it kind of spinning around as it works its way around right there, things can have both a linear velocity, which is how fast it's moving side to side, and an angular velocity, which is just kind of how fast it's rotating. And actually, believe it or not, you can actually take this wrench, and you can now say, well, I can take this big whole wrench and I can boil it down to a single point. So I can take all the mass of this wrench and boil it down to a single point, and that's actually going to be called the center of mass. And as this wrench rotates, it's actually going to rotate about its center of mass, and so its center of mass is actually going to trace out a parabola, in which case all we're really doing is we're boiling all the mass down to the center of it. And if this was a nice linear object like this, then it would be in the dead center of it. Because the wrench has more mass kind of in this direction, then it's going to be a little bit to the left of the center of it. Now, suppose you had like an old school record player or a merry-go-round or something like that, and you set it turning, then it's actually going to have some angular speed, and that angular speed is kind of given this funny looking W symbol. It's going to be a constant. It's going to be 45 revolutions per minute, or whatever, however many turns this thing makes per second. And that's going to be a constant whether we're at the center or at any point along this line right here. But something that's kind of complicated is, even though this guy is going to be a constant, if we picked a point right here and a point right here, well, right here at a certain amount of time, that point close is going to go that distance, and this guy right here is going to go a much longer distance. We even kind of generalize this and say that point is going to take a certain amount of time to go all the way around. This one's going to take a certain amount of time to go all the way around. That time is the same. What that means, though, is the outer one's going to cover a larger distance, and so it has to be going faster. Now, it's not going faster in an angular sense, it's going faster in a linear sense or a tangential sense. So this bug right here might be going pretty fast. This one right out here is going twice as fast in a linear sense. I could kind of draw this guy's velocity vector like this, and this guy's is going to essentially be twice as long if he's twice as far out. So what this boils down to is rotational speed, or angular speed, is different than the linear speed. Now, it does turn out that they are related. If you think about having something that's rotating, then all parts of it must go at that same rotational speed, whether we're talking 45 revolutions per minute or whatever, what have you. The tangential speed is going to depend on the radial distance or how far away you are. We can say that the tangential speed is going to be equal to the radial distance multiplied by the rotational speed, or kind of in shorthand, speed is equal to radius multiplied by rotational speed. And actually this guy has always got to be in radians per second, but don't worry, I'll always give it to you in that. So if we thought about having a radius of 0, so you have a merry-go-round and you're kind of sitting right in the middle, then you have no linear speed. Your linear speed is equal to 0. You're just kind of watching the world go round. And as you work your way further and further and further out, then you're going faster and faster and faster and faster, because this radius is getting larger. That guy is just a constant, so this guy has to increase. So just take a second and read this problem while I draw it out. We have two ladybugs, one sitting right here and one sitting right here. and we know that this guy is spinning at 20 RPM. That's going to be a revolution per minute, so an angle per unit time. And this ladybug right here has a speed of 2 centimeter per second. What you can kind of deduce is both of them are going to share this guy right here, but because this ladybug is twice as far out, she should be going twice as fast, so she should be going 4 centimeters per second. The next concept I want to talk a little bit about is that of rotational inertia, or could even be said rotational mass if you want. And what rotational inertia says is if you have an object and it's rotating, then it tends to remain rotating unless acted upon by some outside influence. Now, I don't know about you, but this looks an awful lot like the linear inertia that we talked about, which said that if you had an object in motion, it tended to remain in motion unless acted upon by an outside force. Looks pretty much the same. And how much inertia something had was kind of dependent on its mass. The same thing is true for things that are rotating, and it's not going to be mass, but actually going to be rotational mass or rotational inertia, which has that symbol I. Now, how much rotational inertia or rotational mass an object has is going to depend on two things. It's going to depend on how massive the object is, just like linear inertia did, and it's also going to depend on the distribution of mass. And it turns out that the further away the mass is from the axis of rotation, the harder it is to rotate. Kind of think about having a bar with some weights on it, and that's going to be pretty easy to rotate. Here we have the same amount of mass, but a slightly different distribution. Now all the mass is relatively far away from the point where you're trying to rotate it, so it's going to be harder to rotate. And the larger that the rotational inertia is, the harder it's going to be to change the rotational state. And this kind of answers the age-old question: is why does a tightrope walker always carry that big rope or that big pole? Well, if you think about it, we've got a lot of mass really far away from the pivot point. That's going to be the pivot point. And if he starts to feel himself going over to one side or the other, then he's just going to jerk up right here, and this thing doesn't like to rotate, and so he's able to pull himself back up and remain relatively stable. Just to kind of drive home the point, consider 3 pencils, 1, 2, and 3, and all these guys have the same mass, and we can rotate this pencil any number of ways. Probably the easiest way to rotate it is going to be about the lead, if you will, right? It's got most of its mass is really close to the point where you're trying to rotate it. We can rotate it about its center, so we can rotate it right here, and it's going to be harder to rotate than case number 1. It's got more mass further away. Probably the hardest way to rotate this pencil is about the eraser. So kind of take a look at this guy right here. We've got the same mass, but now this little chunk right there is really, really, really far away from the point you're trying to rotate it. So it's going to be the hardest to rotate right there. This is also kind of why, if you've ever been working on the side of a house, something like that, you're going to have the ladder, and you're going to extend it all the way up to the very tippy top. And then when you want to go ahead and try to move this ladder, then what you typically want to do is you typically want to lower it back down. So bring this guy down, compress it to right there, move it over to the next little bit, stick it back up, move it down, or put it down, move it, put it down, move it. Now, the reason for that is if you tried to jerk on this guy right here, you've got a lot of mass really far away from you, and it's hard to rotate. So here I have a board, and it has some mass to it. I can't change that mass. I can rotate it several different ways, and it'll have different rotational masses. Take this, for example. I'm rotating it about the center axis, and most of the mass is very close to it, so it's easy to rotate. I can rotate it like this. Now it rotates about the center of the board, and more of the mass is further away from that pivot point, so it has a higher rotational mass. It's harder to rotate. The hardest way to rotate this is to have most of the mass really far away from the pivot point, my hands, and again, not changing the mass, just changing the distribution of the mass, so that had the largest rotational mass. Now, right here we have a table of a whole bunch of rotational inertias for various objects. And so this is going to be rotational inertia, that's going to be mass, and that's going to be radius, in this case radius squared. And this is for a simple pendulum. And essentially rotational mass is just going to be mr squared for a simple pendulum. For a hoop about the center, it's also going to look like a pendulum, so it's going to be 1/2 mr squared. And we have a whole bunch of other shapes. Probably the only one I really care about would be that one and this one, as well as the pendulum. What I want you to kind of take away from this is that it's about twice as easy to rotate a solid cylinder than it is a hoop, because this guy has half of the rotational mass that this one does. And kind of the reasoning behind that is in this guy right here, all of the mass is relatively far away from the point that you're trying to rotate it. And this guy right here, even if it's the same mass, then some of that mass is right here, some of it's right here, some of it's right here, and a very teeny tiny little bit of it is on the outer edge, making it easier to rotate. So if we were to consider a hoop or a disc in a release from rest at the top of an incline, which one's going to reach the bottom first? I guess we'll let my demo show you. So here we go. I have the hoop and I have the solid disc. They have the same mass, though it really doesn't matter. The difference is the hoop, all the mass is located about the outer edge, so it's harder to rotate. So when I release them, it goes a little bit slower. It's just harder to rotate. Now we're going to change gears just a little bit and talk about, well, we've talked about things that are rotating, we've talked about how things can be difficult to rotate. So the next question we're going to ask is, well, how do we get things rotating? And as we get into that, would it be easier to stop the door near the hinge or near the edge for the same amount of force? I hope that you're probably guessing near the edge and not the hinge. The reason behind that is because we're dealing with these things that are called torques, which is going to be a force times a distance. And it turns out that if you try to push a door near the hinge, well, your distance is relatively small, so the amount of torque you can generate is going to also be relatively small. Now, one thing to kind of keep in mind is here it's got a perpendicular symbol on the force, and all that says is the force has got to be perpendicular. I'm never going to give you any forces that are at some weird angles like that, but I do want you to know that if this guy right here is your hinge and you were to push inwards on it, that is not a perpendicular force, that's a parallel force, and you can't shut a door by pushing directly in towards the hinge. Now we do know that the unit of force is going to be Newton, and the unit for distance is going to be meters, so torques are going to be in Newton meters, and they're always calculated about the pivot point. In this case right there, that's going to be my pivot point, so we use like a hinge or something like that. And much like for forces, we could say that if you had a force in that direction, we're going to call that positive. If you had a force in this direction, we're going to call that negative. For some reason, when we talk about torques, it turns out that counterclockwise is positive and clockwise is negative. And you can kind of see that this guy right here is going to generate us a counterclockwise torque, so that guy would be positive. If I pulled on it like this, then it would generate a clockwise torque, and that would be negative. Now, the designation of positive and negative is going to allow us to calculate net torques. So we know that net torque is going to be like net force, where it's going to be the sum of the forces. So we could have torque 1 plus torque 2, and in this case right here, we're going to call this guy torque 1. It's going to be force 1 times distance 1, and we're going to call this torque right over here torque 2, force 2 times distance 2. And one thing we have to pay attention to is this guy is going to be clockwise, this guy is going to be counterclockwise, so they're going to, well, add and subtract. This guy right here is going to be negative, so we're going to put a negative sign right there. And this is really just like forces, where if we had a force of 5 newtons in this direction and a force of 10 newtons in this direction, then the net force is going to be 5 newtons in this direction. The same is true for torques. So let's just get a little bit of practice figuring out some torques. We're looking for the largest and smallest torques. So for this guy right here, the torque is going to be equal to the force times the distance. So that's going to be 10 newtons times 5 meters. So that's going to be 50 newton meters. And I'll make that explicitly positive because it is counterclockwise. This guy right here, the force is still 10 newtons. The distance is 2.5 meters. So we're looking at 25 newton meters. This guy right here, the force is 10 newtons, but the distance is a big fat 0. so the torque is also going to be 0 Newton meters. And last but not least, here we have a force, but it's not perpendicular, so it's not going to generate any torque. It's going to be 0 Newton meters. So the smallest is going to be these two, and the largest is going to be this guy. Now, of course, some real-life applications of this. I don't know if anyone's ever tried to change a flat tire on an old rusty car, but sometimes those lug nuts are just hard to loosen, and maybe what's the best and safest thing to do? Of course, the thing most people do first is they do jump on the end of the wrench, but trust you me, I've busted my shin a couple times. Tapping on it is probably not going to work, but if we use a pipe to make the handle longer, then what we can do is we can take this guy and we can extend it out, and as we extend this guy out, we can maybe apply the same amount of force, but at a larger distance, generating a larger torque, because torque is force times distance, and as we make the distance larger, the torque has to go up. And again, what we're doing is actually something called mechanical advantage, which allows us to play games with force and distance, keeping in mind that there is no free lunch. The amount of work that you have to do is always going to be the same. And what we can kind of do though is we can kind of say, okay, well, here's a pivot point right here, and it turns out that the torque on the first side of the house has got to be equal to the torque on the second side of the house. So force times distance is equal to force times distance. These guys 2's and these guys 1's. And here I'm kind of given the force and the distance, and kind of what I'm looking for is what is the amount of force that I can generate with this guy. So what we can kind of do is we can kind of say 10 newtons multiplied by 1 meter is equal to this new force and 0.1 meters. And so the amount of force that I can generate is actually going to be 100 newtons for my 10 newton initial force. But kind of keep in mind that the amount of work I can do has got to be the same, so I can only move it up a small distance, even though I've got to go up and down right here quite a bit.